All right, let's continue the program vaguely on schedule. As you will be aware, we had to shuffle a few talks around, and maybe you want to know what's coming next, although as Ravi was just telling me, perhaps better to be unprepared because then you have a more open mind. So the program for the next two talks will be Marshall Cohen and Ray Norris. Then after the tea break, the last formal talk will be from Bernie Burke, and then we'll have a discussion session in which I'll try my best to involve everybody here, and we have a few topics which have arisen during the last 3 days which could have further discussion. So I'd now like to invite Professor Marshall Cohen, Emeritus Professor at Caltech, PhD originally from Ohio State University. He then went to Cornell, became involved in solar radio astronomy. Then he was involved in the building of the Arecibo telescope. And then when VLBI was invented, he became one of the VLBI Black Belt gang. Spent a year in San Diego, which is where I first met Marshall, and actually worked on interplanetary scintillation. Then went to Caltech, where he has spent his last 40 years, and is one of the world's experts on VLBI, but has also written the history both of Arecibo and Owens Valley, maybe others I don't know about. So, sorry, Marshall, this was longer than you wanted. Marshall Cohen.
Okay, I can hear the echo, so it must be turned on. Let me say that I was really very pleased when I heard about this meeting to honor Rad and his 1,000 moons. It's been a friend of Rad's for a long time. I think I met him first at Owens Valley. That was when he was there, and I wasn't yet, but I made some visits there, and you were in the basement there working away on a maser, a 21-centimeter maser amplifier that you had brought from Bell Laboratories. And it wasn't working very well. I'm not sure if it ever worked very well. It worked, not well. That's my impression of it. Anyway, masers were tricky in those days. They still are. Nobody uses masers anymore, except probably JPL does at the Deep Space Network, because you get a little bit better noise figure. Now, so the title of this talk is Ignorance Can Be Useful. And we already learned that yesterday, I guess it was, from, who was it? Had that long list of topics. It was Miller, I think. Peter Shaver, there he is, who, number 17 out of 25 of his useful characteristics, one of it was ignorance. And so he already foreshadowed this. And originally, I was going to entitle this talk, Mistakes Can Be Useful, and of course that was number 7 on Peter's list. So everything I could say was already there. Peter simply didn't have enough time to actually go through all of what I'm about to say. So I'm giving you now a subset of Peter's talk. And what do I mean by this? What I mean is that the people who thought about and first designed, went through the rough design and then the detailed design of this dish, were ignorant of something, or you might say they made a mistake or they left something out. It wasn't a mistake of the, what you might call a blunder form. It wasn't an arithmetic mistake. It was not knowing about something and making the wrong assumption. But anyway, that led to the 1,000 feet, whereas a much smaller dish would have worked. And fortunately, they didn't know about the other side of things, and so we got the big dish instead. So let me go through this story now. So what was going on? We're back at early 1958, and the ionosphere was a hot scientific topic. In 1957, the IGY started. The organization for the IGY had started half a dozen years before, and it went on for a year and a half, and the ionosphere was a very big part of that. We heard also how some geophysical studies were part of the IGY. That's certainly true in solar studies. I'm talking here about the ionosphere studies. They promoted 75 ionosondes around the world, including at least one on Antarctica. So they were very serious about measuring what was going on in the ionosphere. And you know, with an ionosonde, it's essentially a vertical radar at low frequencies, and they sweep the frequency, wave goes up, and you'll get an echo from the ionosphere at that level where the local density is the plasma frequency. The plasma frequency at the local level is the frequency of the radar. So you get an echo, say, from 100 kilometers. Then you raise the frequency a little bit, and the echo level goes up because the density goes up as you go up. And I'll show you a picture of that in a little while. Then after a while, you get to a high frequency, and the wave goes all the way through, because if you get up to, say, 100 megahertz, you get no echo from the ionosphere. The frequency's too high. So that means you don't know what goes on above the maximum electron density level, which is typically 300 or 400 kilometers. It's not that you have no information. You had some tantalizing information. There was echo information from rockets and from whistlers. And then a big thing, of course, during the IGY, there were some satellites launched. And this was part of the IGY program, and that had been organized already many years earlier also, except when Sputnik 1 went off, there was jubilation in the Soviet Union and dismay in the United States. And in some ways that was good, because it produced a lot of money and a lot of excitement. And so in a way it was good. The first U.S. Explorer satellite was the Explorer, went up in January 1958, and that one discovered the Van Allen belts. And right after that, interestingly enough, people began talking about putting an ionosonde, a sounder, in a satellite. Put the satellite up high and then do topside sounding, that is, look down on the satellite and measure all the characteristics of the ionosphere up or down to the level where you get penetration. This is just a quick look at the ionosphere. If you look at the blue line, you see the profile of density, a typical profile. There's electron density, there's height, vertical, electron density going to the right. So right here is the peak density, and this is the penetration frequency, if you get the right units. So what else was going on at that time? Well, the military had a great interest in the ionosphere. Why? Because of ballistic missiles. Ballistic missiles were a serious thing. This is the Cold War, and the Soviet Union and the United States had missiles, and they had atomic bombs, and each side was worried about the other. Of course, the whole world was worried. But anyway, it was very important, and there was a great deal of study on it. And the important factor is that the ionosphere is the environment where these ballistic missiles are for 20 minutes or however long they're in the high ionosphere. And even though you might think the ionosphere is pretty much an empty place, which it is, there's ions there, there's magnetic field, there's winds. But still, if you're spending barrels of money on missiles, you could spend a tiny fraction on studying the environment where the missiles will be. And so there was lots of money available for research. One other indication of the military interest is the list of nuclear tests at high altitude. Well, atmospheric tests. First one was in 1945 by the United States. The last atmospheric test was in 1980. It was made by China. And there were tests that were made specifically to study the ionosphere, some of them. And here's this Argus I'll just mention, was one of the last of the series of high-altitude tests, and that was set off in the South Atlantic. There were 3 nuclear bombs exploded above 100 kilometers some days apart, and the precise reason for doing it, these were bombs that were part of what the United States had. These weren't tests of the bombs, they were tests of the ionosphere and what the explosion could do on missiles. And what is it that you could learn on the ionosphere and the effects of nuclear explosion? And it wasn't the thing of putting out a flash which would kill telephone communications. They were specifically worried in that Argus test about killing radio propagation, and also possibly on the effects of putting out enough particles into the ionosphere, changing the ionosphere enough that would affect the missile. They thought that that might happen. In fact, at the end of all these tests, it was found out there's no effect on the missile itself, but there was a lot of effect on radio propagation. And another big thing coming from military interest is ARPA, which is now called DARPA, the Advanced Research Project Agency, or the Defense Advanced Research Project Agency, was founded in February '58 precisely because of the satellite, the Soviet satellite that was put up. And of course, prior to that time, there was a huge amount of American investment and work on satellites and space things, but it was all uncoordinated in a sense. The idea was to bring it all together under one umbrella. So a third place where all these ideas for Arecibo came was from Bill Gordon's background. Bill Gordon was the father of Arecibo. Most of you will have heard his name. Many of you know him, and he unfortunately died a few months ago. His background is in what's called over-the-horizon propagation. The idea here is that here's the spherical Earth, and it was known experimentally that you could, at say, centimeter wavelengths, you could be here's the transmitter, and you could put a receiver over here, way beyond the Earth's curvature, and you get very much more signal over here than you would expect from the exponential decay that you get for propagation around a spherical Earth. And in this famous paper in 1950, Booker and Gordon explained this, and as follows. Each of these antennas is looking up into the sky. They intersect, the beams do. There's a common volume. That volume contains some atmosphere. The atmosphere has fluctuations in dielectric constant. We just call that delta epsilon squared. And so you excite these fluctuations. They act like little dipoles, and they transmit their own piece of energy, and it comes down to the receiver. And the way they described it in this paper was that the atmosphere they're talking about is neutral, and the fluctuations are from turbulence. And so this was the first paper explaining this, and it's still referred to, the famous paper. Well, if you have this over-the-horizon propagation, it's quite easy to see that you could bring the two antennas together and look straight up, and you'd get echoes from the fluctuations in dielectric constant that are there. And that could be the ionosphere, that little patch of common atmosphere. And that's what was in Bill Gordon's mind. It was either January or February of 1958. Take a pair of these antennas, put them in the same place, and get echoes from the fluctuations in the density in the ionosphere. Now, there was other things that are in the background of Arecibo. People knew about the Jodrell Bank dish that was sitting on the ground. Had been built quite a few years before. It was 218 feet in diameter, and it was a paraboloid, and at the focus, well, it was a tall telephone pole, as it were, sticking up, and that could be moved sideways, to give you some limited focal motion. And here's another one that's not so well known, Nature 1957. So this is 8 months prior to Bill Gordon's start of the study. A new form for a giant radio telescope. This is from A.K. Head from Melbourne. And he's talking about a large spherical dish with something that looks suspiciously like what's at Arecibo right now. And here's what Head had. He talked about a large sphere, and he was talking several hundred meters in diameter, which is what Arecibo basically was. And so here's this huge sphere, and it's a little hard to see, but there's some structure which is on a railroad track, and then up above it there's this interesting thing that looks like the Arecibo collector right now, and that aims down at the dish. And what you cannot see, unfortunately, is this B, which is a screen back here, so that when you tilt this off the vertical, you can move the screen over to where you're aiming and get some more piece of the sphere, so you don't do vignetting of the beam on the ground. So this was published in 1957. So here's an example of a pre-Arecibo large dish on the ground. Here's William E. Gordon, died a little while ago, as I said. Here it is, not a very good picture. That's him on the catwalk. If you've ever been to Arecibo, you know about that catwalk. It's quite an interesting place to visit. So here was his idea. He's interested in radio propagation. At Cornell, there was an active radio physics group, nowhere near as big as the group in Australia. Nonetheless, it was active, and a number of people, not radio astronomy people as much as atmospheric physics people, went through that, and then all these years have had careers in mostly the United States. And so there was a lot of interest in the ionosphere in that group. They were studying the local ionosphere. There were several PhD theses written from Alaska. That is, Cornell students would go to Alaska to study the aurora. And Bill's idea was to get at, this is tricky, Bill's idea was to get at the top side of the ionosphere with a vertical radar. It's just like over-the-horizon propagation. So you use a frequency, he was talking several hundred megahertz, much higher than the penetration frequency. You get echo from free electrons, and that's a small cross-section, so you need a powerful system. And they went to work and tried to estimate, tried to calculate what it would take to get that. Here's what they were talking about. They wanted to study the ionosphere up to 1,000 kilometers. Densities, they get almost to 10 to the 6 at the maximum. Above a few hundred kilometers, it's fully ionized. It's partially ionized below that. It would be of interest to study the partially ionized region also. Temperatures, a few hundred to 1,000 K. At these temperatures, the electron velocity is of order 100 kilometers per second, say. So there would be a Doppler shift in the echo. Doppler shift would be on the order of 100 kilohertz. That tells you something about the bandwidth of the receiver you need, and that tells you all about the system and how big the antenna is. And the idea is to measure the density, temperature, composition, motions as functions of height and time. So the question then arises, how are you going to calculate the echo? We needed the fluctuations in the dielectric constant if we're just going to carry on with the theory that we used for the neutral atmosphere. And we got them from turbulence. But what is the equivalent in an ionized gas? It's the fluctuations in dielectric constant, that is to say, the fluctuations in density. Bill didn't know. In fact, no one knew, because the theory was only worked out 2 years later, and it was instigated by what is happening right now with these Arecibo studies. So what did Bill actually do? Well, here's what was known, although Bill didn't know it. What was known is that in 1952, David Pines and David Bohm wrote a paper about the fluctuation spectrum for fully ionized plasma with stationary ions. Stationary meaning just take all the positive charge, smear it out uniformly, and then the material is neutral electrically. Put the electrons in, let them run around at that temperature. What is the echo that you get? Well, it turned out, after a pretty heavy calculation, that I should have probably taken the square root of this, so you get the mean electron density. This is usually written as the square. The fluctuation in the squared electron density is the density itself, divided by this interesting denominator. And so, depending on the value of k lambda, this could go from 1 up to, or down to something near 0. K is the wave number. We're talking about a spectrum here. Lambda d is the Debye length, and it's proportional to the electron density divided by the temperature. Those of you who have studied any plasma physics at all will have heard of the Debye length. In fact, if you've studied chemistry, you will have heard of the Debye length. This is a concept originally put into physics by Peter Debye, who's a chemist, and he was studying other things. So it depends on the value of k times lambda sub d. However, Bill Gordon did not know about the Pines and Bohm paper, nor did anyone else who was working on the project those first few months. Now I have a confession. I was working on the project those first few months. We were talking about the antenna and so on, and I'm not sure if anybody ever asked me about the fluctuation spectrum. If they had, I would have shrugged and said, I don't know. What did Bill do? Bill assumed that the electrons were independent, the individual echoes would be incoherent, and to get the total echo, to get the total cross-section, you multiply the individual cross-section by the number of electrons. Seemed perfectly reasonable. And I know that in April of that year, there was a seminar at Cornell where Bill went through all this stuff, and everybody just nodded. When he put this up, he said, yes, sure, that's it. You have so many electrons, and each one scatters according to the Thomson cross-section. I guess no one in the audience knew about the Debye length. But in fact, this number, Ne sigma, is really the short wavelength limit of Pines and Bohm. If you put in real ionosphere numbers, 10 to the 5 per cubic centimeter, 1,000 K, 300 megahertz, lambda d, the Debye length, is a small fraction of a millimeter, and the wavelength is of order a meter, and so that denominator is going to be bigger than 10 to the 4. And so the intensity of the echo, according to the Pines and Bohm theory, is a factor of 10 to the 4 below what you would guess, just by assuming the electrons scattered incoherently. So the echo is greatly reduced. Well, I'll come to what that means in a minute. What it means, of course, is if they had known that, they probably would have given up because the echo would have been extremely small, although there's more to the story than that. Here's what Bill calculated. The scattered spectrum would look like that. That'd be a Gaussian, and that's the Gaussian, which is the projection of the vertical component of the electron's motion, and they have a Gaussian distribution. And so the width, the half-power width, is about a kilohertz, and this is for a frequency of 400 megahertz and a temperature of 1,000 K. And so this was calculated, of course, and then this width gives you the bandwidth that you need in the receiver. And then the intensity is just the number times the Thomson cross-section. So everything is known about the echo, and then you can calculate how big the radar set has to be. Now this is what they wanted to do. They found out that it's tricky. So to detect 1,000 electrons at per cubic centimeter at 1,000 kilometers, and you want to measure the temperature to some accuracy and the height resolution of a certain amount, and you don't want to make a lot of fancy components, and all of that gives a dish of about 1,000 feet with some error allowed, but not an awful lot. And then immediately, as soon as you hear 1,000 feet, you think about echoes from planets, and echoes from the sun, and echoes from Jupiter, and radio astronomy experiments, and so on. And so in the spring of 1958, there was this big explosion of interest in a 1,000-foot dish. I want to show you the timeline here. I'll come back to this after a bit. So in April, there was a seminar. It's the one I spoke about. In June, Bill Gordon submitted a paper on this to the IRE proceedings. In that same June, there was a proposal to ARPA to get money to design this radar. And from June to December, there was a design study. They came up with a vertical paraboloid, which it isn't, with a depression in the karst region. The karst region was San Sebastian. That's not the current location. And then in October, there was a fundamental thing that happened. Here's the paper that appeared later that year. In November, or in the autumn of that year, there's this fellow Ken Bowles. Here he is. He had been a student at Cornell and had written a thesis on echoes from the Aurora Borealis. And he was working at the National Bureau of Standards in Boulder, Colorado. That outfit died. It's now called NIST. And he heard about the Bill Gordon idea and decided to go ahead and try it using a transmitter that had just been built, not completely assembled, that was in Illinois. It was an NBS transmitter. And I'd like to call your attention to this first sentence. I'll read it. The possibility that incoherent scattering from free electrons in the ionosphere vibrating independently might be observed by radar techniques has apparently been considered by many workers, although seldom seriously because of required sensitivity. So what Bowles says in his first sentence in his first paper is that this is a subject that's in the air. People have been talking about getting echoes from the ionosphere. And I've talked to Ken Bowles, and he has told me directly, yes, he thought about it, but then I've talked to some other people, and they said, no, Bill was the first person to get the idea. And if you look in some of the history books having to do with this topic, they say the idea came from England. So I do think it was what they call in the air, although there was no doubt at all that Bill Gordon got the idea independently. Well, I even shouldn't say that. That was his comment later and what other people said. But, after 50 years, one's memory changes. And it's not that you're lying. It's that your memory truly changed. The story has changed to make it a little more interesting or a little more favorable to you. This is what happens, and happens to everyone. And in the course of doing the research, the paper is based on my paper, I talked to quite a few people, including some famous names, like Ed Salpeter and Bill Gordon and Herb York, who was the first director of ARPA, and they gave me recollections of what happened in the late 1950s and early 1960s, and this is what it was, and he was the first to do this, and so on. And then it turned out, not that those were inconsistent, but I would find out that they weren't exactly right because I went back and read the papers that I could find and the early reports, and in particular, essentially everyone had the time sequences mixed up. That's why I showed you a bit ago the timeline, because what I showed you is correct, because that is according to what the IRE proceeding says on its cover and to what the reports say on their covers. So I went and looked all this stuff up, and I learned that you can't trust what people say. They give you a hint of what was going on, but you have to go back and really look in detail. In fact, that's why I started this whole project, because I realized that I remembered something, and then I realized after that I remembered it incorrectly. And this is having to do with what I was doing at the beginning with Arecibo. So I had my own personal experience with misremembering something. So what is it that Ken Bowles found? Here he is. Oops. And that was in June '66, and there he is on the right. 3 years ago. Well, that's an interesting story too. My wife and I were out on a nature conservatory trip in Southern California. There's a 15 or 18 people there, and who turned up with Ken and Lou Bowles out of the blue. And I had talked to him by email a bit, but I hadn't seen him in 30 or 40 years. So here's what happened. Ken Bowles, in that paper that he just wrote, says he measured the echo strength, and it agrees with what Bill Gordon calculated to within an order of magnitude. It was a rather insensitive experiment, and if you go back and look at what he wrote, you could say, sure, that's about right. It's certainly within a factor of 10, but not within a factor of 2, meaning that the incoherent scatter idea does give the correct strength for the echo. But what he measured had a narrow spectrum right there. According to Gordon's idea, you should get an echo width of about 1 megahertz. And Ken Bowles got an echo width. Again, it was a very bad measurement, and he never gave a number, but it was some kilohertz. So it was 50 times smaller than what had been calculated. Then he wrote some more papers. These are the papers that I'm talking about. There's Phys Rev Letters was the first one where he gave some experimental results. Then there's this AGARD symposium and an NBS report. And in these papers, he does speak of the necessity to compare the RF wavelength with the Debye length. And he does correctly get that idea. And what's happening is that the ion, because the RF wavelength is much bigger than the Debye length, the electrons are trapped by the ions, basically, and you're looking at the electrons bunched around the ions. That's not the right word, of course, but you can imagine it that way. Or someone said you're looking at fleas on an elephant, and the fleas are trapped by the elephant. The elephant moves, you're looking at the fleas. Their average echo is going to be the speed of the elephant, not the speed of the fleas. And so you have to think of the echo as coming from electrons which are bunched around the ions, and the width of the spectrum is governed by the speed of the ions. Now, the speed of the ions is a lot, but we're talking about singly ionized oxygen. This is not hydrogen. So there's a big ratio between the ion weight and the electron weight, and there's about a factor of 100 in the spectrum width that you expect. So I'll show you a picture of that. Well, these are as soon as this came out, then of course theorists began calculating these things, and so there were 3 papers 2 years later. Jules Fayer, Ed Salpeter, John Doherty, and Don Farley, and the result is the spectrum has a flat top shape with the width set by ion motions, and there are also 2 weak lines which are essentially echoes from the plasma lines that are running around in the common volume. Oh, and one other thing. The strength of the echo is the same as what you would get from the elementary incorrect calculation to within a factor of 2. Here's a theoretical picture. On top, you have here this Gaussian, which is what you get if you think only of the electrons moving and forget the ions, or smooth them out. And down on the bottom is the spectrum of the echo from what's called the ion plasma wave, which is from the electrons which are trapped by the ions, and so you get this interesting shape. And these shoulders are due to what is called, in fact, the ion waves. And look at the spectrum width. It's 10 kilohertz, and up here it's a whole megahertz. So there's about a factor of 100 difference in the spectrum width. And of course that means that because the strength is the same on the 2 calculations, it means that this thing here is very tall compared to the Gaussian. So I put the red curve up on top, and it's that arrow in the middle, and it goes up to the next floor somewhere. Now you have to imagine that you're going to design a radar, and first you design it to receive this broad Gaussian at a level of 1. And then you realize, no, that's the wrong spectrum. I'm not going to see that spectrum. I'm going to see this other spectrum. It's an arrow. It goes way up high. It's going to be much easier to detect the arrow than it is the Gaussian. So there's no need to build a 1,000-foot dish. In fact, you could build a 100-foot dish. And in fact, the confirmation of this is given that same year, 1960. They used an 84-foot dish at Haystack Observatory in Massachusetts, Pinio and Company, and they had read all these papers and so on, so they just put the right radar set into their 84-foot dish, and they measured this spectrum. This is an experimental result, and that agreed to the accuracy of what they could tell. It agreed with the fancy calculation. The strength was as you expect, and the width was due to the ions. So all that happened fairly early, and I'm going to go back to the timeline if I can find it. Here we are. So Bohl's experiments in October. In November, the Gordon paper appeared. It predicted that fat spectrum, the Gaussian. Next month, the Bohl's paper appeared, and Bohl's and Gordon both had been in contact, and with all the ionospheric people, all the people involved around the country knew about this. And so, a month later, the results are not, well, that same month, there's a design study, Gordon Booker Nichols, was published, and they had spent the money ARPA gave them, and in this design study, they proposed building a 1,000-foot dish. And this is 1 month after a paper was published in PRL pointing out that to do the particular job for which they wanted, that just to measure density and temperature, they could do it with a 100-foot dish. However, at that time, or early the next year, they went ahead and did more studies. They picked Arecibo, more papers, and here it has to do with the spherical dish. In October the following year, there was a proposal from Cornell to the Air Force to build a 1,000-foot dish. This is now a year after this experiment, when they found out that a small dish would do the job. So that was my first question. Why did they continue to build a 1,000-foot dish when they knew that a 100-foot dish would do the job? And I asked Bill that, and I asked that of Herb York, and I never got a clean answer, but I think the idea must be that as soon as 1,000 feet became the official number, this was before the Ken Bowles experiment, we had all these ideas about doing experiments, and I calculated echoes from the planets, and we studied what we might learn about the sun, and how we might extend some of the radio surveys that had been done, and follow up on the Cambridge and Australian surveys. So we had this whole long list of fancy experiments we were going to do, and everybody was all fired up and very interested. We're going to build a 1,000-foot dish. And so the original idea of just measuring the temperature and density of the ionosphere, that sort of was an afterthought by that time. But why is it that the Air Force, I mean, that might have been the case at Cornell, but what about the Air Force? Why spend some millions of dollars, not very many, by the way, 8 million or something in the end. Why spend $8 or $10 million when you don't even have to build a dish? There are 100-foot dishes that the military owns. We'll just use our own dish. And I told you the answer. We pushed. The Cornell people had the idea that it was good to do. Bill Gordon did talk to the ARPA people and so on, and they obviously had the idea that 1,000 feet would be good. I directly asked Herb York that question. Herb York, incidentally, also passed away this year, so it's going to be much harder to get into these things. I never found the correspondence between Cornell and ARPA, and that's buried somewhere. I even went into the Eisenhower archives in the middle of Kansas. I didn't go. I telephoned them to try to find the ARPA papers, and they couldn't find anything, so maybe Miller or someone will get interested and will actually travel to Topeka, Kansas, and go to the Eisenhower Library and read through a whole building's worth of documents. Anyway, Herb York said something as follows. Well, it seemed like a good thing to do. We've got this small dish, but we've got all this money, and anyway, there's lots of other things we can do. If you build a 1,000-foot dish, I just said with a 1,000-foot dish, you can do radio astronomy experiments, and you can do radar on the planets, but you could also do many ionosphere experiments that cannot be done with a small dish. If you build a 1,000-foot spherical dish that can tilt 20 degrees, then you can move the beam around the sky and watch traveling waves go by. That was something that would be pretty hard to do with a small dish that was really limited in sensitivity. And by that time, they had already known the theoretical results that you could essentially do ion spectroscopy with this thing, because you'd get different echoes according to the magnetic field if you could get your beam perpendicular, nearly perpendicular to the field. And there were other ionosphere experiments, and many of them were done in subsequent years, and they're fabulous. The other thing is they had lots of money. It didn't matter how much they spent. So ARPA must have thought that reverting to a 100-foot dish would be useless. They've got that. It would still be of interest to build a 1,000-foot dish. They had this study. They had this long list of experiments. But go ahead, let's do it. Anyway, it's only $10 million, and we're spending billions. $10 million compared to an atomic bomb or to a missile, that's what they were talking about. That's as much as I can say about that. Let's keep going. Okay. Cornell signed a contract. Here's my question. Why did ARPA go for the 1,000-foot dish? So here's a conclusion, which is sort of conjectural. The 100-foot, at the end of the first paragraph, it says the 100-foot dish was ignored and the 1,000-footer was funded and built. This is sort of the result of a discussion I had with Bill Gordon. Now, Bill didn't know about Pines and Bohm. Pines and Bohm had to do with calculating the echo from the electrons if you smooth out the positive charge. And it gave a very low echo. If you had assumed that the Pines and Bohm result was a good approximation to the real ionosphere, then you would have given up the idea of building a large dish, or any dish, to look at these kinds of echoes, because the echo would be a factor of 1,000 too small. So it was extraordinarily beneficial that Bill did not know about, that is, was ignorant of Pines and Bohm. And the fact that all the rest, I was part of that. I didn't know about Pines and Bohm. So my ignorance was also beneficial, not as much as Bill's. Fortunately, they didn't know about it. ARPA knew about it. Well, once ARPA got involved seriously, they did become concerned. And ARPA commissioned a number of classified studies, plasma physics studies, about what the echo would be. Here's a speculation. You know, a certain amount of history these days is written as what if. It's actually not history, it's speculation. Here's a speculation I'm putting out. So what if Bill had known about Pines and Bohm? He got to the point of seeing that the echo would be very much smaller, or it might be very much smaller. So if he had published that and said, let's calculate the real world, let's let the ions move around, and that might have prompted the theoretical studies. I think it probably would have. That's my speculation. They would have prompted Bowles or Pinio or someone else to make an experimental test. Anyway, in either case, the echo would have become known in a few years. The possibility, all these possibilities would be seen. And I think a 1,000-foot dish or something like it would have been generated in any event, only maybe 10 years later. It's now being replicated. Here's a slide of the FAST project in China. They're building a 500-meter dish. Only 300 meters is being illuminated. There is a, ooh, it should have been bigger. Those of you old enough to remember old movies will know that there was always a Gothic statement at the end. It said "the end." And so that's it. Thank you.
Thank you, Marshall. Question from Miller.
Marshall, thanks. Great,
Thank you.
great result. You mentioned in the planetary radar sequence a lot of things that were done, but there's a solar radar. Was that ever tried?
Actually, solar radar was tried at Arecibo. First solar radar was in Texas, done by Jesse James.
Yes, I know that result.
So you know that result. And a couple of papers were written from Cornell. And Vahi Petrosian, who just retired as professor of physics at Stanford, he did a master's thesis with me on the possibilities of getting radar echoes from the sun. And he worked with me, and then Tommy Gold made some suggestions, and he calculated what you might get back if you had a magnetic dipole on the sun with the axis vertical, and you separate the ordinary and extraordinary rays, and you might get an echo from the top of it. Tommy got him to work out whether or not you might get an echo from shock waves that were coming more or less vertically up in the sun. There was some experimentation done at Arecibo. Nothing like an echo was ever seen.
Yep, get set up. Any more questions while Ray is setting up? Okay, thanks again, Marshall.
You're welcome.